After this lecture, you should understand what an industrial control system is, the typical components and how they work, you will be exposed to a simple example and the basic idea of how an industrial control system functions. Finally, we'll apply this basic understanding to a real industrial control system. One of the goals of this class is to develop your understanding and ability to communicate about industrial control systems. So if you were to be in an interview or in a workplace setting and needed to communicate with someone about an industrial control system, you would be able to understand the terminology they will use and communicate effectively. Industrial control systems is a term that is used broadly. It includes everything from the powering system for the machine to the PLC and software in the PLC that is used to achieve functionality. It includes the instruments. So instruments in this case would be sensors or various types of sensors or smart devices. And it includes even pneumatic components and pneumatic supply systems. Since the idea of an industrial control system is so large and encompassing, it draws on multiple disciplines. So it does utilize ideas from control theory, so the use of feedback loops to achieve a desired functionality, but it also includes power design, because part of designing an industrial control system would be designing all of the powering needs for the system. And it also includes all of the software design. So we're also talking about computer science. So largely speaking, we're talking about control theory, power design, and computer science as being the constituent disciplines for industrial control systems. Each of these disciplines contributes different components and ideas to the machine. So obviously power design contributes the powering system to the machine. Control theory contributes the ideas of instrumentation and actuation. Computer science contributes the idea of programmatically defining the function of the machine in software. Each of these is an integral part of the overall control system for the machine. But each of these also contributes to another typically considered separate but related concept, which is machine safety. So every system, every industrial machine that is produced in the United States and in most countries around the world is required to have a safety system for asset and human protection. Now, a class that was purely about industrial control systems would encompass a deep dive into each one of these topics, including safety systems. But for this short discussion, we're going to focus on instrumentation, actuation, and software. Of the three things we're going to discuss, instrumentation, actuation, and software, you probably have a decent grasp on what software is, but maybe a little less on what instrumentation and actuation are. So we're going to go through some examples of components that would be in each of these categories and discuss what these are. Starting with instrumentation, Instrumentation is anything which provides an input to the PLC. So this could be many different things, but a couple of the most common would be magnetic sensors, inductive proxies, and various types of laser sensors. So laser sensors come in a lot of varieties, but there could be through beam. That's what you see on like supermarket conveyor belts, where when something breaks the beam, it detects that there is something in the way. There are other types of laser sensors that are reflective, and they're actually detecting the number of reflected photons. And there are time of flight sensors, which detect the amount of time it takes for a photon to travel to a distance and be reflected and return to the emission source. So broadly, think of instrumentation as inputs. Of all these terms, when I began a career in the industrial world, I think actuation was probably the term that I was least familiar with. Actuation in general refers to anything that moves. So, a common means of providing motion in industrial machinery is a pneumatic cylinder, an air cylinder. And there's a lot of reasons why pneumatic cylinders are often preferred uh, over servo slides or linear servos, which are also very common as well. But both of those would be examples of actuators. And for this discussion, think more generally so that actuation refers to basically anything that provides an output. Output and input here would refer to things which provide information about the real world. That would be an input, and an output would be something that somehow affects the real world. So, an actuator, like an air cylinder or a linear servo, is going to cause movement at the machine. But even a light that we turn on from the PLC is going to cause something to change about the real world. So, an input is something that gives information to the PLC about the real world, and an output is something that changes the real world. So when we're talking about software in a PLC, typically we're talking about output control, input feedback, input back checking, and data handling. Some of that would be obvious. Output control is the logic that controls when an output would be on or off, or if it was some sort of continuous output like an analog output, to what level is it on. Input feedback would be if you have commanded an actuator to perform some action in the real world. So let's say that you have fired a valve which causes an air cylinder to move. You need to detect that it has moved to the correct location via some magnetic sensor. And that's going to provide feedback to show that the intended function has occurred. Then there's also back checking. So not only will we detect that the air cylinder has moved to the intended location, but there should also be a sensor for the location prior to commanding the cylinder to move. And we would want to see that sensor no longer say that the cylinder was present. So if you have two cylinders, one is a retracted cylinder and one is an extended cylinder, and we have the cylinder currently in the retracted position, and we command it to go to the extended position, we would want to see the extended position sensor come on and the retracted sensor go off. So we're getting feedback from the extended sensor, and we're back checking the retracted sensor to make sure that it's not somehow miswired and just always on. And then data handling is any sort of data manipulation, gathering, and storage necessary to provide traceability for whatever product is being produced. An example of this would be when a car company needs to do a recall on a product. So if a seatbelt tensioner has issues, and those issues seem to be across all models of cars that use this particular seatbelt tensioner, then one of the fundamental things that whatever car company is having this issue is going to need to do is they're going to need to find out which cars have those particular tensioners. And let's say that it's not every tensioner of a certain variety. Let's say that it was every tensioner made from, September 2016 through November 2017 at a particular factory in Mexico. So it's going to be important that that car company has maintained the data for all the cars they've produced to be able to search and find which cars have seatbelt tensioners that match those dates and criteria. Otherwise, they're going to have to recall all the cars released that could have possibly had those in it, had those seatbelt tensioners present. Obviously, that would be very, very expensive. So data handling and manipulation and storage is an incredibly important and integral component of a modern industrial control system. So here's the basic idea. The PLC is going to be programmed to put together some component or facilitate some process, and to do so it's going to have to interface with the real world around it. So the first step is it's going to command some actuation. After commanding the actuation, so let's just say, for instance, that this is a machine that installs the pin on the head, or installs the cap on the head of a pin. So let's say that it has an air cylinder, that it applies air to the backside of the cylinder extends and places the cap on the pin. But to detect and make sure that this has occurred, we have to have a sensor to check that the cylinder has properly extended and back check that it is no longer retracted. After verifying that the action was taken through our instrumentation, we're going to log an internal memory of the actions we've taken and a history for this part in the PLC, and ultimately that history is going to be saved to the database. One of the ideas that industrial control systems borrows from the study of control theory is the idea of a feedback loop. So it's important here to notice how that loop comes into play. At the heart of the loop, we have the PLC. So the PLC generates an output, and this output takes the form of an actuation. So the PLC internally in software turns on an output which causes in the real world an actuator to actuate. This actuation causes a sensor or instrument to register a change. So for instance, a sensor that is placed on the barrel of a air cylinder may detect the magnetic internal device which is used to detect the position of the cylinder. So an actuator then causes a change in an instrument. This instrument is in communication with the PLC as it sends data to the PLC in the form of inputs. So then the entire loop looks like this. PLC causes an output, which then makes an actuator move, which is detected by an instrument, which sends the information about the movement to the PLC in the form of an input. So as you can see, we have a closed loop system here. We command the system to do something, and then we verify that the system has taken the action which we commanded. So hopefully at this point you have a loose idea of the theory of what's going on in an industrial control system. The PLC sits at the heart of it and is programmed to take the necessary actions for the process to be carried out in the real world. It does this by commanding actuators and monitoring those actuations via instrumentation that come to the PLC in the form of inputs. So now let's look at a simple example of a system that could do this very thing. We're going to start by drawing the actuator. And in this situation, we'll be going with our pin capping example, and we're going to have an air. So this is the general symbol for an air cylinder. So what is being shown here is you have some piston rod that is connected to a center body in the cylinder such that when air is applied in this region, so pressurized air comes into this region, it causes the air cylinder to move this direction. Then when pressurized air is applied into this chamber, it causes the air cylinder to retract in this direction. So we have our actuator. The air cylinder is the actuator, but we have to have some way of interfacing the PLC with the actuator. A typical way of doing this is to have a set of valve outputs that are controlled by the PLC across a field bus network. So here we have our valve outputs extend, which when the extend fills this chamber with pressurized air, it will cause the rod to extend, and a retract output, which will cause this chamber to fill with air, which will cause the rod to retract. So on the bottom we have here a fixture. A fixture would just be some piece of tooling which is where we will keep our pins stationary for the cylinder to press the cap onto. Now that we have an actuator, we need some sort of instrumentation to be able to get feedback about whether or not the actuator has performed the commanded action. And in this case, our feedback is going to be given by sensors which are mounted onto the side of the cylinder and will detect the magnetic top of the cylinder rod. So now, when our valve outputs command our cylinder to extend because of pressurized air, this will extend the rod, and this bottom piece of the rod will travel with the rod, and it has a magnet on the back end of the rod which will come into line with this particular magnetic sensor, which is connected to the extended input. So this is our digital inputs, which we will connect to the PLC via field bus. So our PLC is able to command, extend, and retract, and then is able to get inputs to monitor whether the actuator, our air cylinder, has performed the extended or retracted function. So at this point, we need to put the PLC in place, and we'll also put in the database, and we'll add a barcode scanner because we want to know which pin we have placed the cap on, because we need to track the data. And we won't draw a very detailed pin, we're just going to put something as a placeholder there and call it the part. Okay, so we have our PLC database and barcode scanner, but as it stands right now, the PLC database barcode scanner and digital inputs and valve outputs are all disconnected from each other, so there's no means of communication. So at this point, we have to add in the networks. So part of designing a control system is designing the networking for the devices to be able to communicate. So first we will add the field bus network, and we'll talk more about what that means in a second as far as a field bus. Now we'll add the data network. So at this point we've drawn enough to have a complete system. So the field bus network is a very important concept that you definitely want to make sure you're comfortable with if you're going to be interfacing with someone who works in industrial controls. The field bus network is a way to communicate inputs and outputs across distances in a compact format using networking. So we have an Ethernet cable, and that's what this green represents, is an Ethernet cable. And this Ethernet cable is using a field bus protocol. And a field bus protocol could be Ethernet IP or Profinet. There's many different field bus protocols, but what they do is they allow for the PLC and the digital inputs or the digital outputs or the barcode scanner to exchange inputs and outputs. So it allows the PLC to send outputs to the valve outputs, and it allows the PLC to send commands to the barcode scanner like take barcode, and it allows the barcode scanner to send the barcode information back to the PLC, and it allows the digital inputs to send inputs to the PLC. And this is much more efficient than wiring digital discrete wires to the PLC for each of the various inputs and outputs. So this is space saving, time saving, and ultimately it's much easier to debug. So a field bus network is a common idea that is in every industrial control system that is manufactured today or has been manufactured in the last 20 years. So we have the following loop to be able to command the PLC, to command and get feedback on the actions the PLC requires. So based on the basic idea we presented earlier, the PLC generates outputs, which then cause an actuator to perform some action, which then causes a change in the real world, so it puts the cap on the pin, and the magnet comes down and is now in line with the magnetic sensor, which detects that change in the real world and sends the, so this is an instrument, so the instrument detects the change in the real world and transmits that change via digital input across the field bus back to the PLC. So the PLC commanded the action, caused the outputs to fire, which made the actuation happen, which made the real world change, which was detected by the instrumentation, which then sent digital inputs across the field bus back to the PLC. And this is the typical way that a control system is implemented in the real world today, via PLC, field bus, valve manipulations that cause actuator movement, detection through instrumentation, input transmission across the field bus back to the PLC, and that closes the loop. Now, we also have other things that sit on this field bus network other than just inputs and outputs that are digital. Like we said, this barcode scanner can transmit the barcode back. But ultimately, we can represent a barcode in a string. A string would be a digital encoding of letters, right? So it's still digital, therefore it can still be transmitted on the field bus back to the PLC, and the PLC can transmit information to the barcode scanner, such as request to scan. So the way that this machine would work is an operator would insert a pin into this machine, and the PLC would command the cylinder to press the cap onto the pin, and when the cylinder reached the extended position, it would be sent back to the PLC. The PLC would recognize that its action that it had commanded had been fulfilled, and it would then log that the cap had been placed onto that particular pin by reading the barcode to know which pin had been capped, and then it would send the barcode of the pin and the completed cap time to the database. So that way, let's say that this was a third-party company and they were making pins for BIC, and BIC received a shipment of pins and several of them did not have caps. And BIC was saying, you made a mistake to this third-party company. The third-party company could then turn around and check their data and say, no, we think that in transit, someone took the pin caps off, because we have data showing that for each of these pins we have a barcode scan and a time of completed cap installation. And this is the general format and way that every control system in an industrial machine works today. So this example should be somewhat familiar to you because it was used previously in the semester. So as we watch this video, I'll talk through it and discuss a few of the things that you should understand based on our lecture so far. So this robot is about to pick the housing from the pallet and is going to place it onto a fixture in the back of the machine. This fixture then is going to clamp the housing to the fixture and allow for a pressing operation to occur. So the cylinders that you should pay attention to are these rotary cylinders at these two corners of the fixture. They're going to rotate and clamp the part in place. Now, that rotation and clamping action is caused by a valve output, just as we discussed previously. And there are sensors on this cylinder which detect the presence and movement of the magnetic sensor, of the magnetic flag on the barrel of the air cylinder. So first, the robot is going to pick the pinion and place it to the fixture. And the grippers are also driven by pneumatics. When it places the housing, and those rotated and locked, the robot continues to place things. As I said, these grippers are driven by pneumatics, so you hear the air escaping. Hear that? There's a burst of air. Now this is a press that is pressing these components into the housing. Now it's complete, so the robot's going to go back and grab it. Those cylinders are going to retract. The operation is complete. So just as we discussed, we have a PLC that sits in this cabinet in the back. It is waiting for the robot to say that the housing is in place, and when it does, the PLC commands these cylinders to rotate and to clamp the housing in place, and it detects that that has occurred via sensors, magnetic sensors that detect the magnetic flag on the barrel of the air cylinder. And that's how the robot knows that it is okay to retract away, because the PLC tells the robot that it has securely fastened the part to the fixture. Then when the robot goes to grab it again, if the robot grabs the housing and did not wait for the PLC to give the all clear, it would be trying to pull the part off of the housing while these clamps are still in a clamp position. So instead, the PLC tells the robot to remove the housing after the clamps have been commanded to open or retract, and the sensor has confirmed that the retract operation has occurred. At that point, the PLC has commanded and verified that it has occurred, and the PLC notifies the robot that it is clear to remove the part from the fixture and return it to the pallet. Hopefully this information will be useful to you in the future, as some of you no doubt will apply for jobs working potentially in automation or industrial controls. But even if not, if you work for a company that even has an industrial sector, so for instance, if you say you worked for Volkswagen or Ford or Eastman Chemical, then they have operations that are largely run by PLC. It's going to be important that you're able to communicate with the people who work directly with the industrial control systems.